got my water. Worth about $5,000 in space.
So we have Martin Elvis from the Harvard Smithsonian Center for Astrophysics, and he's going to talk about astronomical prospecting of asteroid resources.
Yes, I'm going to be a worked example of one of the knowledge gaps that JL just talked about. The where and the what of the asteroids are things that we have to know. So the basic problem is that not every mountain is a gold mine, and that's true of every asteroid too. In fact, the really valuable ones are quite few and far between. Only a few %, in fact, are actually worth mining, and that's straightforward. This is a simplified plot, but basically, overwhelmingly, the asteroids are stony, and that's boring for a first use of space resources. Eventually, no, but mainly we're after the few % that are carbonaceous, of which only a fraction are rich in water, based on meteorite studies. And the smaller fraction still that are metallic, and again, a smaller fraction of those are actually rich in platinum in the sense of being about up to 10 parts per million, and that's much richer than a mine on Earth, but you would only select out those. So those are the ones we want to go for. Now, astronomy has taught us a lot of this, and meteoritics too. It's taught us an awful lot about asteroids. We wouldn't be thinking about mining them without the science behind it. The things that are important are in yellow for the miners. The rest aren't important. The trouble is, all of this, as JL was saying, these have been done for science, which is great for understanding the solar system, but it's not optimized for mining. Asteroid miners are going to need spectral types. Just at the stony, not stony level would be great. Even carbonaceous versus metallic, that would be good too. But we're going to need thousands because, as I said, only a few % are actually resource rich. Of those, only a small fraction, depending on your rocketry available, are actually accessible with large payloads that you will need to mine asteroids. So we need to assay about 100 asteroids to find one that's resource rich. That's demanding because you need unconstrained launch windows, as JL mentioned, and you have to have enough inventory behind you to convince your investors that this isn't a one-shot deal, that you're building an industry here. You need a good back catalog. So you need dozens of rich near-Earth objects, not just any old asteroid, has to be near-Earth to be accessible. So you need thousands of accessible ones which have at least a simple carbonaceous, stony, or X-type classification. How many asteroids do you need to go to assay whether they're valuable or not? This is an exercise in binomial statistics that I did with Thomas Esty, an undergraduate. Basically, if it's 1 in 10 that are carbonaceous, which is about right, then you need to go to 30 different asteroids to find one that is rich in water, right? But you don't know it's carbonaceous. If you don't know it's carbonaceous, then you have to go to 100 because it's 1 in 40 chance of it being rich in the water you want. And that's a barrier to actually doing the work. But if you had a simple spectrum and you could say it's not stony, you're down to about 1 in 4, and you need just 10 probes. Well, that's enabling. That's cutting the cost of exploration by 90%. So this is incredibly valuable information to a mining company. And that's what astronomy can do for the asteroid miners. Well, how are we doing so far? Not very well, because it's not done for asteroid mining. There's no point in doing this bulk work if really for science. There probably would be an outcome for it, but it's harder to justify. We get maybe 2,000 of these near-Earth asteroids have spectra. If you just pull from the JPL database, this is against absolute H magnitude, then the ones that have types are a minority, and in particular in the band. In fact, you have to get to 50 of them, you have to go up to a delta V of 6.4 kilometers a second, almost the median value for near-Earth objects. But in particular, the range of sizes that are interesting for asteroid mining is roughly 20 to 100 meters. And you can see there that by far the bulk of those do not have spectral types. This is the plot of potentially hazardous objects. Just to illustrate, most of the near-Earth objects we now find, this is the where, the orbits for them are bad, so that they are effectively lost. If you have an orbit code from the Minor Planet Center, this is from Galace et al., a paper of 2015, worse than certainly 4 or a bit worse, then you will not find that asteroid again on its next apparition or subsequent apparitions for 10 years at least we looked at. It'll be too faint and too uncertain in its position on the sky. It would be out of the field of view of any single typical large telescope imager. So most of those are lost, and again, that's the region that's most interesting for mining, and the overwhelming number of them will not be possible to find again. This is bad news. Pretty bad news for asteroid science, I think, as well, but we should concentrate here on the mining. I'll just justify that statement about the size range. This is the integrated number size plot, and this is the sweet spot for asteroid mining, because if you go to larger sizes, there are just too few of them to find any significant number at low delta V. Each one is very valuable, but there are very, very few of them that are accessible. And if you go smaller, then they're not even worth $1 billion, so who'd get out of bed for that, right? That means the numbers are between 20,000 at the large end and 20 million at the small end. So it's going to matter very much what the shape of that curve is in that range. It's a huge steep slope, and it's very ill-determined in that particular range. The above that and below that are well known, but we don't really know how to extrapolate in between. So the good news is that astronomers can solve these problems. The WHERE, of course, requires precise orbits, tracking asteroids over as long an arc as possible, with as great highest precision as possible. There's 2 levels of precision we care about. One is enough to find them again, and the second is enough to actually rendezvous a spacecraft with them. We've thought about the first question a lot. We haven't thought about the second question much yet. So, of course, this means astrometry. Accurate astrometry. The what means spectroscopy in some form or another, colors at least, of spectra of different asteroids, at least to get the simple stony, not stony classification, and that's spectrophotometry. We're thinking that the Gaia satellite, which is, of course, an ESA mission, there's some details of it. It's released a catalogue of 1 billion stars to 10 milliarc second position, which is 10 to 100 times better than anyone's had before, especially at those faint magnitudes. That means every field of view of every imager will contain a good number of these stars, so it provides a very good reference frame for any measurement of the position of an asteroid. You need to be able to take advantage of that, of course. We're running some simulations just to see how much that alone will improve the positions of the asteroids at their next approach. It's quite complicated when you get into the details. We won't go there. It only works, it's only useful if you can actually get asteroid positions at that accurately. That means you must, in a very short time, to reduce the blur on the sky, you must get a high signal to noise, like 100. And then you can go from half-arc second seeing down to 20 milliarc second or thereabouts accuracy for your asteroid at any one moment. And then you must do that over and over again. So that means a large telescope, at least 4 meters. I'm going to talk about a 6.5 meter we hope to use for this in a moment. Okay, so the what, different color, rocks have different colors. I think you know this mostly in the audience. And this, of course, is the standard way we classify asteroids now, with particularly near-infrared spectroscopy, and you see the bumps and wiggles give you a lot of diagnostics. What's the best way to measure their colors for the asteroids that miners are interested in? So the near-infrared, which is the standard now, is very good in that it's a very clean window, nearly 100% transmission in much of the near-infrared band. And that's good, plenty of diagnostics, but often forgotten is that the sky is extremely bright in those wavelengths because of very high altitude hydroxyl emission lines, thousands and thousands of them. And you could go to very high spectral resolution and look between them. That's been attempted by cosmologists who'd love to do that. It's been found to be very difficult. And since we find things at 20th magnitude, now most of these near-Earth asteroids are found around 20th magnitude or a bit fainter even, and then they fade. We have to be able to get to that kind of magnitude, and in the near-infrared, 90% of these become inaccessible to spectroscopy after a week. So we've got to find another way. This is the best way, except it doesn't work for the objects we're interested in as miners. So we go to the optical, backwards in technique and backwards in information content. We agree with that, but it gives enough information. Most importantly, it gives you that pyroxene olivine absorption band starting around 0.8 microns. If you see that, it's dead certain it's a stony asteroid, and I'm happy to be contradicted. I'd love to know better, but I'm an amateur in this, relatively speaking. And if you don't see it, it's probably not stony. So we need big telescopes. There's some technical details about integration times, and it gets very depressing on 3 or 4 3-meter telescopes or smaller. There's a whole lot of issues involved in getting a lot of time on a big telescope. I want to emphasize for the non-scientists here that what's very important here is that we need high professional standards. These are 1% type measurements to extreme accuracy, and you don't do that by getting a guy off the street. You have to have someone who's trained in this kind of work. So I'll just give a couple of slides on where I'm actually working on this now, how I'm approaching it. JL is working on a different approach, concentrating more on the low resolution optical spectroscopy. I have access to the 6.5 meter Magellan telescopes, and so I'm with one particular instrument on there called PISCO. It seems to be particularly well suited to this work. So that's the 6.5 meter primary mirror of Magellan. This is the PISCO layout. It's a 4-color imager, taking simultaneous images in G, R, I, and Z. And that's very useful for exactly this way. It wasn't designed for this asteroid work, but it turns out to be very useful for it. So we get where and what with one instrument. That's what the data looks like. I've colored them in to make it look right. That's 4 images taken simultaneously of the same galaxy. And you can see that it looks sort of the same. But of course, that's very deceiving. When you combine 3 colors, you get this image of the radio galaxy Centaurus A, and you see lots of subtle variations in color. And you can, if you measure those accurately enough, about 1% precision in the photometry, then you can make maps like this. This is a simulation from Elvis et al. But you can see the different symbols, different types of asteroid, and that they lie in different places in these diagrams. They're distinguishable, but only if you get very high precision photometry. So we have 1 or 2 observations already, but we got a serious integrated night coming up in December. It's spread over, the whole night is actually spread over a week of observations, so we can get more objects. It'd be easy for me to scale this without much effort to a few hundred per year, 200 or 300 per year. And if we could get a lot more time on this kind of instrument, we could probably scale that to 1,000 a year quite easily. But that requires some investment on that part. But I think this is one of the ways in which the asteroid prospecting will come of age. And I hope to give some actual results at the next EPSC. So, there, Pal, yes. There's an awful lot we don't know about them, absolutely, and I would love to. There's a great need for a lot more scientific missions to these asteroids, and I'd like to make many of those cheaply. And I think that will actually be enabled by the technologies required to go prospect them commercially too. So we should piggyback the science off the great developments coming in that area.
Just repeat. So Patrick Michel was just saying that the spectra outside is not necessarily diagnostic of what's inside.
Yes,
it might have a different spectral type.
The famous example of 2008 TC3, which we got a spectrum of before it landed on the Sahara Desert in Sudan, and the two didn't match up the way we expected.
I have one comment. Okay, just one quick comment that you can take photographic plate archives and mine them for asteroids and get pre-coverage. So this problem of losing asteroids is not as hard as it sounds. You can find these asteroids again in older data.
However, we're finding things at 20th magnitude, and they're small.
Yeah.
So in order to be found in those photographic archives, which probably are 18th magnitude mostly, then you have to be 10 times brighter, so 3 times nearer. So the volume they have to go through, or this cross-sectional area in their orbit is at least 10 times smaller. So it's not very likely individually. You have to have a huge archive. But maybe there are such archives.
Baldwin Observatory Latvia has a 25,000 plate archive. And
There you go.
I'm really trying to get this funded to mine this plate archive, so I'm just putting that up there. Okay.
What a good idea.
Okay.
I had also a comment about the Gaia mission, and I agree, we need surveys not only to avoid losing these asteroids, but Gaia is not only doing astrometry, it also gives colors, or more precisely low resolution spectroscopy, but again, down to magnitude 20.7, 20.5, so it's for the...
The Gaia photometry should be very useful also for getting precision photometry for the asteroids, I think.
Not for the 20 meters, and I agree with you, even the photographic